This is a video about our paper on promote-based personalized federated learning. First, let's introduce some background about federated learning. Federated learning is a distributed machine learning framework that uses edge devices to collaboratively train a global model while preserving data privacy. The training objective of federated learning is to collaboratively train one single global model with distributed data. By training the model locally, federated learning emphasizes security and privacy concerns, the limited computing resources of edge nodes, and communication overhead. The goal of personalized federated learning is to collaboratively train several personalized models with distributed data. Here, there are two clients A and B, where A primarily includes data labeled as 4, and B primarily includes data labeled as 6. After federated learning training, both A and B use the same model, which is not optimal for each client. Uh, in personalized federated learning, each client will have its own distinct model, typically more suitable for their specific characteristics of client. For example, the model for client A is more adept at distinguishing data labeled as 4. Currently, personalized federated learning has some solutions. The general approach is to extract public knowledge and inject it into personalized models. Commonly used techniques include layer-wise partition, regularization, model interpolation. However, these methods typically focus on the model level, ignoring the uh, data level. Uh, this oversight may limit the enhancement of personalized adaptation between the aggregated model and the local dataset. Therefore, we are exploring the possibility of helping the classification tasks by introducing prior knowledge related to the distribution of client data into the original data. In this context, we consider using prompts as representatives of our prior knowledge. Consequently, our objective is to learn a personalized prompt delta for each client as prior knowledge. The prompt delta I is also trained using local data, thus representing certain prior knowledge. Specifically, we designed the following training steps. Step 1. The parameters of the prompt on each client are updated with the local data, while the entire backbone is frozen. This is done to encode prior knowledge related to the distribution of client data into the prompts. Step 2. After the training for several epochs, the prompt parameters will be frozen, and the backbone will be begun to update for a fixed number of epochs. Step 3. When the training process of all clients is completed, they send the trained backbone to the server, followed by the aggregation operation conducted by the server. Step 4. The aggregated backbone will be broadcast to every client to replace the old backbone stored locally. This part provides a more detailed explanation of training process of our algorithm. There are some results of experience. Table 1 provides a comparative analysis of PFEDPT's highest accuracy compared to baseline method on evaluation datasets and various settings on CIVA 10 and CIVA 100 datasets. Particularly in non-ID settings, PFEDPT consistently achieves the highest test accuracy. The performance of PFEDPT can be attributed to the effective use of promos in each client, significantly enhancing the backbone model's performance. Similarly, PFEDPT can also enhance the performance of other federated learning algorithms by using promos related to the client's data distribution. Visual promos simplify the fine-tuning of the client's backbone, assisting federated learning algorithms in achieving privacy personalization. Take a look at the left side of the chart. It displays the attention map of the last year in VIT and CNN. The first three rows show that fit average focused on the key features of the raw image. The fourth row includes images with additional promos added by PFEDPT's parameters. Both PFEDPT plus VIT and PFEDPT plus CNN shift their attention to these promos, helping gather client-specific knowledge and improving their model's performance. We generate 100 different color images and feed these color images into PFET models for different clients with various promos and visualize their last MLP layers output embedding. We project them onto a two-dimensional plane. The chart in the upper right console shows that with visual promos, you can distinguish between different client representation species. In conclusion, we design and implement a novel PFL framework named PFEDPT. It gives the aggregated local model information about the local data distribution and can integrate with other federated learning methods to boost their performance. We also conduct extensive experiments to evaluate the effectiveness of PFEDPT. That's all. Thanks for listening.